What's up, guys? It's Christopher Moss, and this is going to be Chapter 3, Acids and Bases for Ochem 1. Alright, take a second to look at the materials that we'll cover today. On our left are from Gen Chem II, and on the right is what we're going to be covering today. Now, we've learned Arrhenius acids, Bronsted-Lowry acids, and Lewis acids so far. But the most that we'll cover for organic chemistry is Bronsted-Lowry acids and maybe a little bit of Lewis acid bases. On the right side are some general classifications of how they cover. Lewis acids and bases encompasses all types of acid-base reactions, where Lewis acids are the electron pair acceptors and the bases are the electron pair donors. Bronsted-Lowry acids are defined as proton donors, bases are defined as proton acceptors, which applies for most of the acid-base reactions. Arrhenius acids and bases, strong acid, strong base, react together violently to make a salt and water. In general chemistry, we used chemical equations like the one above to depict the acid-base reaction. However, in organic chemistry, we also need to emphasize the movement of electrons and the bonds forming and breaking that are involved. In Chapter 2, we learned that the full-tipped arrows indicate the movement of an electron pair or two electrons, where the starting point is the base of the arrow and the tip of the arrow indicates the destination. Now, in this reaction, we know that the hydroxide anion forms a bond on the hydrogen atom on the hydrochloric acid. This is described by the arrow, base of the arrow starting at the lone pair of the oxygen atom and going all the way towards the hydrogen atom on the hydrochloric acid. Now, we also see that the bond between the hydrogen and the chlorine atom breaks as this happens. This is shown with the arrow starting from the bond and ending at the chlorine atom. As a result, our chlorine atom gets 4 lone pairs and forms an ionic bond with the sodium cation. Our hydroxide, which newly forms the bond with the hydrogen, becomes the water. Now, this is also a good instance to point out that this is an Arrhenius acid-base reaction. We can also see that our hydrochloric acid is our Bronsted-Lowry acid, as it donates the proton to the sodium hydroxide, which is our proton recipient, which as a result gives us the conjugate base, sodium chloride, and our conjugate acid, water. Now, it's kind of hard to see the Lewis acids and base reaction in this one, but sodium hydroxide here is our Lewis base, which because of the donating an electron, and our hydrochloric acid being the recipient is our Lewis acid. Alright, a bit of a review for pKa's. pKa is a logarithmic scale measuring the strength of an acid, or what I'd like to say is the probability of a proton dissociating from an acid. Now, strong acids, usually inorganic acids like hydrochloric acid, sulfuric acids, typically are expected to dissociate completely and have a very low pKa of -9 for sulfuric and -7 for hydrochloric acid. Organic acids, on the other hand, are typically weaker. Weaker acids dissociate partially, which means not all of the acids dissociate completely, some remain intact, and their pKa as a result are higher, ranging. A good example would be acetic acid with a pKa of 4.75. On the right is how we calculate pKa and the Ka values, which are taken during equilibrium. Why is pKa, the strength of an acid, so important? That's because in an acid-base reaction, the equilibrium favors the stable product, other words, a weaker acid. From the previous slide, we know that the pKa decreases as the strength of the acid increase. In an acid-base reaction, we have an acid and a conjugate acid. By comparing the pKa of the two acids, we can determine if the product or the reactant will be favored. Take an example with the reaction on the right, an acetic acid with a pKa of 4.76 reacting with sodium methoxide. Our product will be sodium acetate and methanol. The acid, like I mentioned earlier, is acetic acid. Our conjugate acid is methanol. If we take a look at the pKa values of both of them, we can see that methanol with a pKa of 15.5 or 16 for some of your textbooks is a lot higher than our acetic acid. Since the equilibrium favors the weaker acid, in this case, the reaction will be product favored. Now, this is important to learn some of the exceptions that you'll learn later on in the chapter. On the bottom, we have 1-butene reacting with a very strong base, sodium amide. The acid-base reaction will commence, taking the proton off the 1-butene, making ammonia, our conjugate acid, and I can't even remember what the sign is called. Now, if we take a look at their pKa's, 1-butene has a pKa of 25, while ammonia, our conjugate acid, has a pKa of 37. Since ammonia with a pKa of 37 has a higher pKa, indicating it's a more stable acid, the reaction will be product favored. Now, it's nice and all that we have our pKa's given to us, but how do we determine the favorability of the acid-base reaction without a pKa given? One way to determine it is by seeing the stability of the conjugate base. In General Chemistry II, we learned that a stronger acid has a weaker and more stable base than the other. Introducing ARIO. ARIO is an acronym standing for atom, resonance, induction, and orbital. They are the basic guideline to use when we compare the conjugate bases for their stability. A, the type for atom, is the first step we do in ARIO, where we compare the atoms which loses a proton. When an acid loses its proton, typically it is left with a negative charge. This step determines whether the atom is good or bad at stabilizing that negative charge. Now, when you are comparing two atoms in the same period, or the same row in a periodic table, like carbon and oxygen, the atom with the higher electronegativity is considered more stable. In this case, oxygen, being more electronegative, is more stable. However, if we have two atoms in the same group, or the column of the periodic table, the larger atom, or the one lower, wins. This is because the larger atom size helps stabilizes the charge better. A good example would be oxygen and sulfur. Both oxygen and sulfur are in the same group, but the larger sulfur atom is better, making a stable base, creating a more acidic acid. Resonance. Well, this one's kind of self-explanatory. Hope you guys practice a lot from chapter 2 because you will be required to know how to do this one. So this one's really straightforward. Say we compare ethanol and acetic acid. Ethanol has no major resonance structures. In comparison, acetic acid has 2 resonance structures, 1 and then 2. This allows the electron, the negative charge, to be distributed among 2 oxygen atoms. The general trend that you may see in your practice problems is, the more resonance you have, the better the stability. However, this has to be taken with caution. Take, for an example, phenol and acetic acid. Phenol has a pKa of 10, while acetic acid has 4.75. Now, phenol has 4 resonance structures, while acetic acid only has 2. So this kind of debunks the, oh, I have more resonance structures, so I must be more acidic. Well, unfortunately, this is where quality beats quantity. If you take a look at the resonance structure for acetic acid, the negative charge is distributed between 2 oxygen atoms, while in phenol, it's 1 oxygen atom and 3 carbon atoms. Turns out, carbon is not the best atom to have a negative charge nor a positive charge. And you would rather have 2 oxygen atoms hold the negative charge, having a more stable base. The I in ARIO is for induction. This is simply how the abundance of an electron withdrawing groups, commonly a halogen, can help stabilize the conjugate base. So, as you can see here, the more electron withdrawing group, which I just drew using chlorine atoms, helps you stabilize, makes it a better acid, or create a more stable conjugate base. However, this is also where you have to be careful, as the position of that withdrawing group also matters. The effectiveness of the electron withdrawing group gets weaker as it is placed further away from that anion. So, a lot of the trick questions you'll see is you'll have the same number of withdrawing groups, but one is like placed farther, one's placed closer. So, the closer it is, the more effective, and you'll have a stronger acid. And finally, orbital. This one, I'm just going to keep it simple for you guys. The closer the electrons are held to the nucleus, the more stable. So, in a bond, we have hybridized orbitals, sp3, sp2, and sp. sp, with the most S-shell characteristic, has the smallest orbital, and it is closer to the nucleus. So, if we take this is a good example where we look at the hydrocarbons. Butane has a pKa of 50. Butene with a 1 pi bond at that end has an sp2. Has a slightly lower pKa, but it's extremely high. However, butane with an sp orbital has a pKa of 25. Although they are all high, butane has the lowest pKa, and it is the easiest one with deprotonate if you have a very strong base. So keep that in mind. Now, I'm sure you guys will get tired of using ARIO over and over. So here are some of the common pKa values you should remember. I wrote some numbers on the side that you are recommended to memorize, like sulfuric acid being the strongest one that you'll use is -9. Hydrochloric acid is -7. Water is 15.7, so it's usually like the midpoint for you guys. So butane, or this one is called alkynes, which is the sp ones, 25, and ammonia with 38. 4 and 5 is just important because, at least within UNLV, it always shows up as a trick question, so always keep an eye out for that one. Alright, I know it's been a lot, so take a quick break on you guys, pause the video or something, and alright, we're back. In an acid-based reaction, when you run the reaction, you have to also consider the acidity of the solvent used. Now, the solvent you use should be able to surround the reactants and facilitate their collisions without interfering with the reaction. What does that mean? It means that it should not undergo create a side reaction, which it will happen, but it should not be favored. Common solvents like water, methanol, and acetone all can be protonated or deprotonated. So, a bad example would be, let's say you want to protonate acetone using a very strong acid like sulfuric acid. If you have moisture in there like water, what will happen is the hydronium ion, which is a higher pKa than the protonated acetone, will be favored, which creates a lot of byproducts and it will reduce the efficiency of the reaction. So, A better example for this would be, let's say you want to protonate an ammonia. You use an acetic acid, which has a lower pKa than ammonium, so you know it will be favored. Water is used as a solvent, and the reaction is undergoed. Hydronium ion has a lower pKa both to acetic acid and the ammonium ion. So there is no questions, it will be very unfavored, it will not be created. So in this case, it is a good solvent. The same goes for bases. So if you use a base that is stronger than the hydroxide or its conjugate base, it will be favored and it will create a byproduct of hydroxides. So a good example of this would be, say you have an acetate anion and you use water as a solvent. When you react it with water in the side reaction, it will recreate the acetic acid and the hydronium ion. However, if we look at the pKa of water and the acetic acid has a lower pKa, hence being very unfavorable, and the reaction will not happen as much. Now, a bad example would be using, let's say, sodium amide and water. Sodium amide will act as a base to strip the proton from the water, and it will create ammonia and sodium hydroxide. In this case, when we compare the two acids, we see that ammonia is a lot more stable than water, which makes the reaction favored to the product side, creating a lot of byproducts that we don't want. What's the key takeaway? When you're running a reaction, check to see if any of the reactants and products react favorably with your solvent. So basically do an acid-base reaction with your reactants and see if it does any if it is favorable. If it is, you need to choose a different solvent. That's why you don't want to use this acid that is stronger than the conjugate acid of water, and that's stronger than the conjugate base of water. So choose your reagents and your solvent carefully. Alright, so the solvating effect. I think we covered this a little bit in Unit 1 when it comes to boiling points, but it has a similar issue with pKa. What the solvating effect is, when you have a sterically hindered molecule, it prevents it from having intermolecular interactions. In the form of boiling point, it prevented you from having that intermolecular interactions, which reduced your boiling point. In acids, it also has the same effect. When you have that conjugate base, the negative charge can somewhat be stabilized with the intermolecular forces. However, with the sterically hindered atoms, it is a lot harder and it is less stable, which makes its pKa get higher with the more unstable base. A little more about Lewis acids. I'm not sure if your professor will cover this a lot, but at least in my summer session we did, and it is pretty important as it shows up later in Ochem. So, common Lewis acids you'll see in this course are group 3 elements like boron and aluminum. What's so special is that they only have 3 valence electrons, and to have a formal charge of 0, they typically have 3 bonds and no lone pairs. However, the lack of lone pairs with that creates an empty p orbital, which is extremely good at attracting electrons. Why? Is because you'll later learn that electrons have a tendency to move to electron-rich regions to an electron-deficient region, a concept that will haunt you back in Chapter 6 and onward. Now, a good example we kind of showed you earlier is, let's say, water, which has 2 lone pairs, attack that trifluorobromide, a Lewis acid. So water in this case is our Lewis base attacking our Lewis acid tribromo-fluoride. This will make our product, which it looks weird at first, but it is our Lewis acid base product, which the oxygen atom forms a bond with that electron deficient boron, creating this, I forgot what this is called. Alright, well, that's all that I have to cover for this unit. Feel free to leave any comments and corrections, please. It really helps to improve the future slides that we'll make so that it's better accommodating for what you guys need. Alright,